Yes, hi, this is George Direction again. Today I would like to talk about how to approach problems in convergence or divergence of series. So, how we will do this? I will first state all the rules for checking if a series is converging or diverging, and then I will do a few examples. So, also I will show you how you should approach these problems. So first of all, when you get a problem, first you check if the series is alternating or non-alternating. Let's leave the alternating and we'll come back later. So now, if it's non-alternating, we have these rules here. The geometric, check if it's a geometric series, also if it's a P series, also if the limit of the an does not exist or is different than 0 as n goes to infinity, then the series is diverging. Then we have the integral test, and then we have the comparison, and finally the limit comparison test. So that's the order that you should start checking your, the convergence or divergence of a series. Okay, because geometric and P series are the easiest series to identify if they are convergent or divergent, and the rest it follows. So now let's go to alternating series. So here we have three cases. A series can be diverging, a series can be converging but not absolutely converging, and finally the series can be absolutely convergent. So now alternating series are series that have positive and negative terms, and first of all, if you have that the absolute value of the series is decreasing, and also the limit of the Pn as n goes to infinity is equal to 0, then the series is absolutely converging. And then for checking if a series is absolutely converging, diverging, or just simply converging, you have two tests, which are the ratio test and root test. If you go to the absolute value of the alternating series, of course, in order to check if this is converging or diverging, of course you can use all these rules for non-alternating series. So that's a brief theory and let's say a guide on how to approach these problems. And now I will do some problems. So first example is the series from 0 to infinity, pi to the n over 3 to the n plus 1. So, it's easy for somebody to see, since you have the n and the n here, that means that it's most probably, these are numbers, pi and 3, so that means that most probably this is a geometric series. You just have to work a bit. So because here you have plus 1, you can take the 1/3 outside, and the rest you can write it as pi over 3 to the n. Okay. So, and now because pi over 3, so and this is a geometric series, okay. So, and because p over 3 is greater than 1, so that means that this series here diverges. Okay, the second example is this here. So we have the series 1 plus 2 to the n over 3 to the n. So again, because you see this number and this number, the 2 and the 3, and you see the n and the n, so that refers to a geometric series. You just have to work a little bit again on it. So, I mean, this here, if you divide everything by 3 to the n, you can write it as 1 over 3 to the n plus 2 over 3 to the n over 3 to the n over 3 to the n. So this with this cancel. And what do you have? Now, you know, obviously you have two geometric series, the 1/3 to the n and the 2/3 to the n. So both, you know, this is the A for the first series, the 1/3, and the A for the second series is 2/3. So both of them, they are less than 1. So that means that both these series here converge. So these series here are converging. So, and now what we have to do is we have to find the sum of these series. So in order to find the sum, you just have to use that the sum is equal with A over 1 minus R, where A is the first term of each series, of the geometric series, and R is the ratio between two consecutive terms. So for the first one, the first term is 1/3, and the ratio is also 1/3, so it's 1 minus 1/3. So this here will be 1/3 over 3 minus 1, it's 2/3. And if we take out the 3's, this here will be equal with 1/2. So the first series converges to 1/2. And now let's do the second series, the 2/3. So it's again the same thing. So we said that the sum should be equal with A, the first term. So here the first term is 2/3 over 1 minus the 2/3. So that should be 2/3 over 3 minus 2, so it's 1/3. So the 3 with the 3 cancel. So we have that this here goes to 2. So the whole thing goes to 2 plus 1/2, which is equal with 5/2. So now let's try to find the integral, let's try to find if this series here is converging, the 1 over the 4th root of n. So obviously this is not a geometric series, this is not a P series. If you take the limit, it will go to 0, so it's inconclusive. So what's next? Either integral or comparison test. I believe that this should go by integral, because if you find the integral of 1 over x to the 4th root, so from 0 to infinity, or from 1 to infinity, so that should be equal with I mean, this we can write it also as x to the minus 1/4. So the integral of this is x to the minus 1/4 plus 1 over minus 1/4 plus 1. So this will be x to the 3/4 over 3/4. So, and now if you want to take the integral of this from 1 to infinity, that should be, I mean, if you put infinity first, so if you take the definite integral now from 1 to infinity, if you take the infinity first, so all these will be infinity, and then if you put whatever x1 here, so that should give you 1 to the 3/4 over 3/4, so that should be minus 4/3. So this is actually infinity, so that means that the integral diverges, so that means that this series also is diverging by the integral test. So we have the series 1 plus 1/8 plus 1 over 27 plus 1 over 64, etc. So if somebody looks carefully on this, you see this is nothing else but a P series, where, because you can rewrite all of this as 1 over 1 to the third plus 1 over 2 to the third plus 1 over 3 to the third plus 1 over 4 to the third plus the general term, it will be 1 over n to the fourth. So because the P here is equal with 4, so it's greater than 1, so that means according with the P series test, this series is converging. So thank you for taking the time to view this video, and I hope you find it useful, and bye for now.